Sir, can you hear me?
Yes, please.
Thank you. Assalamu alaikum. Thank you and good evening. The title of my paper is A Novel Family of Class EF and Class E/FnM Inverter for Improved Efficiency. I am Ratil Hasnat Ashik, Assistant Professor, Green University of Bangladesh. So in this presentation, I will be talking about Class E inverter first, before going into the Class EFnm inverter. I glimpse over the basics of Class E inverter, so give you the context, and then I talk about my contribution in this paper. So the outline of this presentation will be the background, the objective, the proposed converter. We'll see the circuit, the operations of the converter in brief, and finally we'll discuss the results of our experimentation and simulation, and also our future plan. So basically, this is a Class E based configuration, and Class E is a very popular, especially in the low and mid power region operations. And the popularity of Class E is mainly due to 3 or 4 reasons. First off, the compact sizing. As you can see, the number of components is very low. So that gives you a very high efficiency and very low loss in terms of switching and conduction losses. And they have a very clean operation. That means their EMI footprint is also very low. So the circuit has basically 2 parts. On the left, as you can see, the input inductor, which we call it the DC input feed inductor. And there are a lot of literatures on how we design an input feed inductor. Basically, we can make it a very high value to ensure that input current is a DC and low input ripple current, or we can include this input DC feed inductor and combine with the resonance circuit to operate in the resonance operation. So if we look at this, if we say the circuit has basically 2 modes of operation. The first mode, where the input DC feed inductor is charged, energy is stored in this inductor, and the switch is on. So energy circulates, energy is stored in this input DC feed inductor. And in the next mode, this energy is being transferred to the right. That means the resonant circuit. And the resonant circuit here is basically includes the resonant inductor LR, resonant capacitor, and the input capacitor, which also includes the the parasitic capacitance of the switch and also the output load. So if you look at the switch voltage, as you can clearly see, this is not a single frequency. This is basically a multiple of frequencies operating here. So this is the switch voltage. So this switch voltage is fed into the resonance circuit. So as I said before, the resonance circuit is acting like a filter. So it filters out all the frequency except the resonant frequency, and it is also converting the DC input, because this is just a single pulse. So it has a DC average voltage or DC voltage. When you feed it into the resonance circuit, this becomes an AC through the resonance circuit. So this is basically the main operation of the Class E inverter. And what we do here, we basically do the first harmonic approximation. So through the first harmonic approximation, we assume that from this switch voltage, only one single frequency transferred to the resonance circuit, which is that means one single frequency of energy is being transferred to the load. But the Class E has very big disadvantage, and that is the very high peak switch voltage. That is also, say if you give a 10-volt input, the switch voltage might go up to 3.5 to 5 times, depending on the circuit configuration and depending on the circuit components. So it can go up to 5 times the input voltage. So if the input voltage is 100 volt, that means your switch voltage is 500 volts. So you really need a very high rating switch. So this type of switches also have other types of losses. So that is contributes to lowering the efficiency of the converter. So this is the main problem with Class C inverter. So to reduce this switch voltage, to improve the situation, what we do, we enhance the classic configuration. This is very old, basically. So this configuration basically we call this class EFn, where n defines a harmonic of the resonant frequency. So what we do in a class EFn inverter, we add an extra resonance circuit. So if you look now, this is the class EFn inverter, and there are multiple resonance circuit here. If you see the L1C1, this is a resonance circuit. And apart from this circuit, this is also an extra resonance circuit here. And this resonance circuit can also be added in the main resonant tank, where is with LS and CS is our main resonant tank. So we can add this extra resonance circuit in the main resonant tank in series or in parallel. So there are different types of configuration. You can add it in series, you can add it in parallel, and each type of configuration have different type of impact on the operation of the circuit. So there's a whole lot of thing going on here. So we need to we need to look into every aspect. We need to compare the operations, we need to compare the efficiency, we need to compare the losses. So only then we can tell which configuration is better for us. And we have not gone there yet, but we will be there eventually. So in this configuration, in this here, so this is the class EFn inverter. But yet again, class EFn inverter is 20 years old now. So this inverter has other types of problems, like the lower efficiency at higher duty ratio. So this, the switch is here. This switch has some duty ratio operation. So if in any case you want to increase the duty ratio, that also lowers the efficiency because the switch is on for longer time now. If the switch is on for longer amount of time, that means the conduction loss is higher, and also this makes a higher loss. Also, this also increases the switching losses. So what we want to do here, also a light loading condition. If the load is very low, if you have a very light load condition, in this light load condition, basically the circuit nearly goes into the unstable region. This is a very common issue with the buck and boost, other type of converters. So what we do here, to improve this situation, so we want to improve this situation. So the main objective is to design an inverter with higher efficiency at higher duty ratio, as this was the problem with the class EFn inverter, and at very light loading conditions. And secondly, we want to offer a higher power. As I have said before, the class E is mostly appropriate for low power region, or lower medium power region. So we want to improve that range. We want to increase the power deliver capability of this class E configuration. So we want to increase the power deliver capability. And finally, we also maintain the stability that is offered by other previous class E and class EFn inverters. So to have these objectives fulfilled, what we do, we add an extra resonant network, which we call now LP and CP is our basic primary resonant tank, and LS/CS is our EFn. In our class EFn inverter, we add this tank. Now we are adding an extra resonant tank with the third resonant tank, this LT and CT, combining LT and CT. And also what we are doing here, we are delivering this power to the secondary through a multi-winding transformer. So the multi-winding transformer, why multi-winding transformer? Because it will be built on a single core multi-winding transformer. So it will help us to reduce the size, to reduce the magnetic losses, to make a compact. As I said before, it's a very low component count device circuit. So if we can reduce the transformer size, our total size of the converter will be very small. And we have other different type of applications, like in laptops, in chargers, and LED lighting. So we need to keep this size really small. So we want to build this transformer in a single core. So this multi-winding core transformer will really help us to achieve this purpose. So what is happening here? The input switch voltage is basically transferring the single harmonic. Say we have a switch voltage here, and the primary resonant frequency is 100 kilohertz. So we are delivering 100 kilohertz power to the secondary through the primary resonant tank. Now this is the second harmonic. So this is the 200 kilohertz switch resonant frequency. The 200 kilohertz resonant frequency is being bypassed through this resonant tank. So this helps to reduce the peak switch voltage, but also because you are now bypassing the secondary harmonic, so you are losing a lot of power. So to compensate that, what we do, we transfer the third harmonic to the third LTNCT, that is third resonant tank. So that helps us to improve the delivered power to the load. So first thing we have done, we have simulated the circuit in LTSPICE with the most appropriate platform we have thought about. And we have simulated the circuit, we have seen the waveforms, and we have different types of outputs here. Like the input current, the input we have got about input current ripple of 11.22%. But this input current ripple is basically totally dependent on the input feed inductor. So if we can increase the feed inductor, we can reduce the input ripple current. On the other hand, if we increase the feed inductor, that means also increasing the size of the circuit board. So there's the compromise we need to really make. And also, one of our purpose was to the switching, soft switching achievement. We have achieved the soft switching, which you call zero voltage switching at turn on and turn off. So we have designed two circuits here. The EF23, that means the secondary resonant tank is tuned to the second harmonic, and third resonant tank is tuned to the third harmonic. Or we have got EF32, where the secondary resonant tank is tuned to the third harmonic, and the third resonant tank is tuned to the second harmonic. So we have tested both of the circuits and see their operation in simulation. And also we tried to simulate that, tried to experimentally tested the circuit. And our results in experimental section and simulation section are pretty similar. And at this moment, at this stage, we are very, very happy with the result we have got. And the switch voltage and the peak switch voltage, the other ratings are very similar to the simulation, at least very close to the simulation results. Now, this is a comparison. If you see the deviation is quite small and quite remarkable. And we hope that if we can, in the next step, we'll be able to go forward with this type of converter and for extension. So our future plan is more comprehensive experimental research with varying parameters to dig deeper and define the operational limit. So we are offering this inverter. So we need to know what maximum power we can offer this circuit with. So we need to see that. And also we want to incorporate the piezoelectric electric transformer to change change the magnetic components with the piezoelectric transformer. So because PET is very small device, so if you can change that, so you can change the magnetic components with the piezoelectric transformer. You can change the resonant tank with piezoelectric transformer. So basically, we can reduce the size of this total circuit. Thank you very much. If you have any question.
So, any question from the audience? Thank you very much. Any question from the audience? Okay, Professor Rajak, it's your turn now.
Yes, actually, I'm curious about your hardware implementation. So we saw some result, but do you have any circuitry and what kind of, so what is the duty cycle?
All right, so we have, for this type of inverter, there is an optimum duty cycle that comes from the theoretical analysis. So class EF, say for class EF32 inverter, the optimum duty cycle is 0.4, and for EF32 is around 0.6.
Okay, so
it's around 0.5.
You are using MOSFET, right? You are considering?
Exactly, right.
Okay, so what is the switching frequency?
Switching frequency is around 200 kilohertz. 220, I think.
Okay, so that means you have a very high switching loss also.
Because it's a ZVS, zero voltage switching, as I've shown.
Okay.
So we have gone to reduce that part, but still zero voltage switching doesn't mean its switching loss is completely zero. It's near zero. So,
okay, so did you analyze any THD or power factor?
This is actually as you see, this is a 5-watt device, 5-watt inverter. So according to industrial standard, so if you go above 10 watts, then the standard IEEE standard needs you to add a power factor correction converter. So this is only a 5-watt inverter. For this application, we have not added any power factor. We have not done any power factor part, and also we have not added any controller circuit here. This is a plain running raw. So in our future endeavors, we will add this controller circuit, and maybe if we increase the power, we will add this power factor. We will consider that power factor correction improvement case.
Okay, so the possible applications in the industry.
Exactly, yeah.
Okay, that is from my part.
Okay, so thank you for your presentation. Now, my question is, what is the output frequency you are talking about? I think it's in megahertz or kilohertz range, isn't it?
No, sir. Actually, yes, I got the point. So actually, basically, this class A inverter is used for operational, used for amplifier or we use it for inverter. So here we are applying for an inverter. So the output frequency is similar to the resonant frequency of the converter, right? So there's 200 kilohertz.
200 kilohertz. Okay, and if you go to the circuit, I am curious about the coupling strength. What is the coefficient coupling between these?
This will be a transformer. So coupling strength will be very high.
Very high.
So
Okay,
yes. So
so trans
we
ratio
build
is
it as
one
a
is to one. Trans ratio is 1:1.
trans ratio is 1:1. Yes.
Oh, so
No,
how
no. So
about
sorry. Trans ratio. I need to see the paper.
okay?
uh, we actually tested do different types of trans ratio to see the effect of that.
So I think your output is being filtered by L0 C0 part, isn't it?
Exactly right.
Because in the input you have two resonant tank, so raw output will have two different frequencies, isn't it?
Right, sir.
So finally you are selecting one of them from the output.
Right. Right. We are
So
filtering. Yes.
yeah, so from two frequencies you are selecting one. So how about the losses?
Yes, actually the cutoff frequency is here around 100 kilohertz. So basically, because if you see here, if we plan to increase, take the output as a DC output, DC power, so that will help us to increase the total power output, and the filter circuit will eliminate the unwanted frequencies from there. Now there is a problem. If we apply if we apply the AC voltage, so there will be some distortion. But if we take it, if we use a rectifier and use that power, the DC power, then there will not be any problem with the shape of the output waveform and so on.
In that case, it will not be an inverter, so it will be a DC-DC converter, isn't it?
Yes, but yes, exactly. But there's some problem with the output waveform shape. But we are working on that part, on the filter part. So if we can manipulate the filter efficiency to some extent, then probably we can use both. Maybe we can use a multiple output at the same time to deliver the power to different loads.
I am also curious about the hardware implementation, because making a transformers and all these things, uh, it adds some complexity in the circuit, isn't it?
Yes,
Because this
exactly.
transformer you proposed, it's not commercially available.
No,
You need to make it.
it's a custom built transformer.
Yeah,
It's a
yeah.
custom built transformer.
So
Okay, thank you very much.
it's a ferrite core transformer, right?
Yes,
Yeah,
sir.
fair.
Ferrite transformer,
Yeah,
commercially
because of
available Ferrite transformer.
yes.
So, did you have done anything? Have you done anything in the lab about the construction of this transformer?
Yes, actually, this testing all were done in UK, where I was there in few months in March. So all
Okay.
tests were done there. So I just after this corona situation, I have just gathered the results and came out with this
Okay.
presentation.
Thank you. Thank you very much. So we
Thank
can,
you.
I think, proceed to the next presentation.